Thank you very much, and thank you to Cambridge Public Health for inviting me. Whoever designed the programme is obviously trying to keep you on your toes, because I'm going to take you from the macro right down to the micro. Since June, I've been the director of the PHG Foundation. PHG stands for Public Health Genomics, we're based down near Addenbrooke's Hospital, and I've got I'm going to talk about people, populations, and genomes. Just to say my background, I'm neither a clinician nor a scientist. My last sort of 20 odd years has been spent at the intersection of science, ethics, and public policy. Most recently at the Nuffield Council on Bioethics, which is where I met Carol for the first time. And I think that's probably to what I owe the pleasure of speaking to you today. So do I advance this by pressing a button of any kind? There we are. Okay, so just a couple of slides about the PHG Foundation. Many of you here, I hope, know the Foundation. We're a health policy think tank with a focus on genomics and related technologies and how they can be used for better, more personalised healthcare. And the Foundation was established in 1997 as the Public Health Genetics Unit, but since 2018 it's been a linked exempt charity of the university, funded by a mixture of philanthropy, grants and commissioned work. This is our vision: a society that makes the best possible use of advances in life sciences to promote health and improve the prevention and treatment of disease by making responsible changes in health policy and the organisation of health systems. And our mission to achieve that is very neatly, I think, encapsulated in the tagline, which I wish I'd invented, but I didn't: making science work for health. And it was the tagline, I think, that really drew me to PHG in the first place, because I think it very pithily expresses the confusion of technical and practical, or factual and normative considerations that characterize what I'm going to describe as public health genomics. And in fact, the ambiguity that's contained in this phrase is one of the things that I want to address in what I'm going to say. Just to clarify, we don't do primary research at PHG. Our focus is really on the normative conditions of innovation in healthcare: the rules, regulations, policies, people, practices, institutions, etc., that are necessary to, in the words of the tagline, make science work for health, or equally importantly, to prevent premature, misplaced, or harmful innovation, in fact. So, on the earlier slide, I said our vision is of better, more personalised healthcare. So I wanted to ask the question, why should personalisation be a goal of public health policy? A number of answers can be given to this question, but the most obvious, I think, is probably that people are diverse, and they differ from each other in significant respects that are both inherent and contingent, and that affect states of health and disease they will experience during their lives. Well, there are some things from which all people will benefit as people: fresh air, clean water, temperate environment. Treating all people as though they are the same may do them both a moral injustice by not respecting their differences, and it may lead to concrete harm or material disadvantage. On the other hand, more personalised prevention and care can be more effective, can lead to a reduction in overdiagnosis and overtreatment, and show respect for individuals as persons with distinct interests and preferences of their own. It can maximise the non-conflicting liberties of each person and make better use of resources overall. And I wanted to stress the sort of historical dimension of this and the importance of two dimensions of the historical context in which I think it's appropriate to evaluate these propositions about the value of personalisation. One is the current state of what I call the sort of epistemic context, the current state of knowledge about the distinctions among people and their significance. And the other is what I call the socio-technical context, our ability and willingness to put those knowledges to use. So to begin, I want to look at the first sense of making science work for health, namely making it work as opposed to not work. That is, making it useful, or in the language of technology and innovation, making it productive. The founding intuition of public health genomics is that human health is conditioned by the interaction of a number of diverse factors, but an important role in this is played by the genome, the complete complement of DNA in each cell that is inherited from each individual's progenitors. So at any point in the life course of an individual organism, their phenotype is conditioned by the interaction of a number of factors to produce a particular successive state out of all of the possible states that were previously available to it. So the phenotype at time 3 is a modification of the phenotype at time 2, just as the phenotype at time 2 is a modification of the phenotype at time 1, produced by both inherent and contingent factors, governed by chance and necessity, circumstance, behavior. And I've included stochastic factors there, not apparent chance or determinacy, not really to advert to a kind of metaphysical influence, but rather just to recognize the limits and the phenomenology of current scientific knowledge here. So because human biological constitution is well adapted to normal human environments, and because humans have a peculiar power to adapt their environments to suit their biology, the genomic contribution to health is often occluded. But rare monogenic or Mendelian disorders offer clear examples of the effect of variations in genotype and tend to be selected against either naturally or deliberately, for example, through prenatal diagnosis and pre-implantation genetic diagnosis, which both limit their transgenerational, intergenerational transmission. But there is a spectrum rather than a sort of what I think Tom Murray called the two-bucket view, between diseases that result from genetic variation and diseases that are caused by environmental factors, toxins or infectious agents, for example. And the example that's often given, although maybe slightly hackneyed now, is that of phenylketonuria, which can cause severe mental impairment in infants, and it's caused by a buildup of the amino acid phenylalanine, which is present in most protein-containing foods. And it's considered a genetic condition normally because phenylalanine is very prevalent in the diet, and the variant that causes the failure of metabolism is fairly rare, about 1 in 10,000 births, I think. But if you consider a different set of circumstances in which phenylalanine was rare in the diet, and the variant was very common, and it could be very common, of course, because if it weren't deleterious, it could very easily be conserved through evolution, then the condition would presumably be considered one that is toxic. But in reality, so genetic factors are probably implicated in all diseases, and even some would say in injuries, to the extent that genetic variation has been associated with accident proneness and risk-taking. And there are a number of studies available on that. So the question I think that we wrestle with is really how far down this pyramid we can go to disentangle the different factors involved in the conditioning disease states and to make them tractable to interventions. I'm going to talk very briefly in each case about just 3 pieces of work that PHG has been involved in. The first one is the European Profit Project, which is a project to produce a personalized prevention roadmap for the future of healthcare in Europe, rather grandly, in the form of a strategic research agenda. So with colleagues from Madrid and Spain, our team's contribution has been to identify research into biomarkers in 3 disease areas: cancer, cardiovascular disease, and neurological conditions. And at PHG, we did the cardiovascular disease. The numbers on the left refer to the numbers of papers that were identified with relevant biomarkers in a 3-year period. But it's pretty clear that there were a lot prior to that, but the number is actually increasing. And the thing to note about that is that there is quite a lot of heterogeneity in terms of the biomarkers that are studied. So most studies focus on different biomarkers, probably, I'm sure, because researchers have an interest in identifying new variants. And many of the studies look at more than one biomarker, but you can see from that in terms of primary prevention, there's quite a preponderance of genetic biomarkers in the research. I mean, we can come back to what might be the reasons for that in a minute. But the ambition of personalized prevention, then, as expressed through this in this project, is to lift, square, and extend, to borrow the sort of tagline of a 1970s advertising campaign, the curve that depicts or represents the average course of life today. So we're having identified these biomarkers. The next stage of our work is to establish evidence for the clinical utility of the biomarkers that have been identified in the first part of the research. Probably just to note that actually, I mean, amongst those, the most common biomarkers, genetic biomarkers that we found are single nucleotide polymorphism SNPs, and identified through genome-wide association studies. Individually, these have a very small effect on disease risk. So it's probably most useful then to look at their collective impact. And if you put them together, it's possible to generate what is known as a polygenic risk score. And I'm going to go and talk about the work that we've done in this area, briefly looking at polygenic risk scores or scores that are derived from the analysis of SNPs taken together. So polygenic scores of SNPs associated with polygenic diseases are put together in a polygenic score model. And each of the identified variants within the model is assigned a weight or effect size based on its strength of association with the disease or trait in question. And variants, therefore, with a stronger association receive a higher weighting in the model. The weighted values are added to give a calculated measure which functions like a proxy biomarker for genetic predisposition to the disease trait. Development of a polygenic score model specifying a particular selection of SNPs and their weights is used then to create algorithms that can be used in clinical practice to calculate a risk score. That's the theory. Just a fortnight ago, we've published a series of briefing notes on unlocking polygenic scores, and these are available on the website. It's really just to kind of explain what we see as the current state of this field. Polygenic scores potentially have a number of uses in primary, secondary, and tertiary prevention. They include targeting appropriate screening, informing choice of intervention, clarifying diagnoses, and providing information to individuals to inform their own life choices. While there continues to be a lot of interest in the use of polygenic scores as part of healthcare, there are certainly now many uncertainties remaining and conflicting messages regarding readiness for implementation. Among other things, the terminology around polygenic scores remains confusing, and it's often unclear what is being proposed for implementation, how it may be used in a healthcare pathway, or indeed how it should be regulated as a medical device, whether each component should be regulated distinctly or it should be regulated as a whole test, jointly or severally, if you like. Polygenic scores can be can be used by themselves, or they can be combined with other markers within a multifactorial risk prediction model to give what is known as an integrated risk score. And those other biomarkers may include more conventional things like blood pressure, cholesterol, and risk factors such as age, BMI, family history, and other potentially a range of other things. And because however, the genomic factors are, by hypothesis, invariant over the life course, they may, in fact, turn out to be among possibly the most accessible eventually, though not necessarily the most informative component of an integrated risk model. And just observe on this that although a pattern of SNPs is largely personal and has limited relevance to living relatives or future generations, there may be patterns that are more characteristic of certain ancestral groups or subpopulations. So among some of the ethical and social issues that need to be considered in the design of PGS applications are potential concerns about bias and inequalities resulting from their constructional use. I've got another slide now that refers to climate, because I just want to give you a couple of slides on work that we've done in relation to genomics and heat. I said earlier that the role of the genome is often hidden because of evolutionary adaptation to the environment, but one area clearly in which the environment is changing at an increasingly faster rate is in terms of climate. And in that respect, evolutionary adaptation may begin to fail to keep up, which will mean certain populations facing new adversities. The optimum temperature for human habitation varies from region to region based on the averages that people living in that region experience. So it's not absolute. The optimum is not absolute for all people. However, human bodies generally have a critical temperature, which is, I think, a wet bulb temperature of about 35 degrees C. And they shouldn't be exposed to temperatures above this for extended periods. However, there are now inhabited areas of the world where these temperatures in excess of that, are seasonally common. And this figure, which is not quite as nice as the one, quite as nicely drawn as the one that James showed earlier, shows the average annual excess deaths due to increased heat from 2000 to 2019, and that's at a, although it's difficult to see here, at a spatial resolution of about 0.5 degrees squared, which is about 35 miles by 35 miles at the equator, less towards the poles. Of course, mortality increases with cold temperatures as well, but human beings are better at managing cold temperatures through deliberate adaptations to the environment. What are the benefits of genomic research in this area? Now, we've only looked at heat, but there are potentially other areas, but this seemed like a kind of way into the question of environmental genomics for us. Because thermoregulation is a highly conserved process in human evolution, and perhaps the reason for that is, as I said earlier, human capabilities with regard to controlling their physical environment and adapting behavior which limits the pressure on physiological adaptation. But there is evidence that people respond differently to heat stress, despite common environmental factors. And studies of exertional heat illness, which is a result of inability to thermoregulate during physical activity, have shown this amongst military personnel and athletes. And I think we might all remember Daniil Medvedev at the US Open earlier this year, who warned rather resonantly that a tennis player is going to die at some point owing to heat the US Open. So we know that genomic factors play a role in a range of responses to heat, including thermoregulation, heat acclimation in response to environmental change, and heat damage response, and the response for coping with the effects of both internal and external temperatures. But a greater understanding of the biological pathways involved could potentially result in interventions, new diagnostics, new therapies. And biomarkers, if we can identify them, could confirm, for example, whether or not symptoms that are being experienced are a response to heat stress or to something else. And importantly, I think, to help identify those most susceptible to heat illness and to severe outcomes, and allow the prioritization of prevention and care. But for any of the biomarkers that we've talked about to provide a health benefit, it must have utility, and it must be incorporated into a test that is useful in practice. And the second part of the profit research that I mentioned earlier involves looking at clinical utility for the biomarkers we identified, where tests have been taken up into guidelines, health technology assessments, or cost effectiveness studies that rely on a prior evaluation of an aspect of clinical utility. But there's no clear, consistent, and universal method for evaluating clinical utility. I've included an example here of a framework for evaluation developed by the CDC's Office for Public Health Genomics. And this is one which underpinned the evaluation of genetic tests in the NHS for a long time. This assesses both the analytical and clinical validity of the test and its clinical utility, along with ethical, legal, and social issues. So it gives a fairly comprehensive assessment. But assessing utility, of course, isn't straightforward. It may mean different things to different people. Personal value of testing for an individual may be different to the value it has, for example, for a clinician or for a health service commissioner. Different people may place different emphasis or different value on type 1 and type 2 errors, for example, in different contexts and at different times. But regardless of the approach taken, it's important to assess the test as a whole and not merely the technical quality of the assay. And I think that's the important message and the thing that PHG has consistently insisted upon. And that is to assess it in its proposed use setting for a particular purpose and within a defined population. And here's a number of a program of work looking at genomic biomarkers and a number of reports that have been published in this area by PHG. So far I've been talking about making science work for health in the sense of securing clinical or personal health benefit from its application. And this is what the majority of the work that I've referred to so far has been mainly concerned with. But in the next 8 or 9 minutes left, I want to turn to the second sense of making science work for health in order to raise some broader ethical questions about the personalization paradigm, if I'm allowed to call it that, and the public and private interests it served. So for most of my career, certainly, I've been working implicitly in the anticipation that genomics would transform routine healthcare, that whole genome sequencing, for example, would reveal the hidden causes of common morbidities and body forth a new era of predictive medicine. And indeed, it's made some very significant advances in tracking down factors that contribute to rare and undiagnosed conditions and to our understanding of complex diseases. However, I think there's perhaps a more powerful force of transformation breaking on us now, and it's not merely genomics that will be responsible. It's the potential of massively expanded use of surveillance, data, AI, and information technologies across biomedical research and healthcare that has, I think, the potential to reconfigure this area of human endeavor. And it's these that can bring or can act as exponents for genomic and other forms of knowledge within healthcare. Integrating data from a range of sources ranging across the technical, the social, and all points in between will give rise to a number of confusions. For example, confusion between research and clinical care, or between social life and healthcare, leading to concerns about medicalization of everyday life and activity. And this understandably gives a reason for anxiety. And this is what I'm going to talk about. In the few minutes left, I just want to speak about the ethics of technologies of personalization as a goal of public health. So coming back to where I started. And to do this, I'm going to take as my reference a talk given in 1957 at the Harvard School of Public Health by Sir Geoffrey Vickers. I don't know how well known this paper is. I'd be interested to know. I came across it cited in a book on the right there, Healing the Schism by Kerr White, former Deputy Director of Health Sciences at the Rockefeller Foundation. It's a sort of mea culpa on behalf of the foundation for its part in producing a sort of two-culture division between public health and clinical medicine over 100 years ago. Vickers is a sort of polymath and interesting character, to me anyway. And at the time of this lecture, I believe he was the secretary of the Medical Research Council, but also a lawyer, public administrator, and systems thinker. And in the talk that he gave, he offers 4 answers to his titular question: what sets the goals of public health? First is that the goals of public health reflect the dominant needs of time, what he says, the dominant needs of time and place, with, he says, a more or less significant time lag. And he's quick to observe that the needs depend on their recognition as needs. And he makes it clear that this recognition is the result of a prior conflict between needs fighting for satisfaction and how it's been resolved in the past. So, as he says, our goals may be not responses to the future, but protests against the past. Second answer he gives, and I think this is perhaps the most interesting from my point of view, is that technology, or what he calls techniques. This lecture was published both in the New England Journal of Medicine and in Lancet. It's rather quaintly called Technique in the British version and Technics in the US version. But anyway, he says his second answer is that technics sets the goals of public health. And that's important because techniques require us to adopt particular disciplines often that potentially reconfigure social relations. And if we refuse these, the techniques may not work or may not achieve clinical utility. As we know, many perfectly promising technologies fail. On the other hand, if we accept those disciplines, we have to accept the constraints that they place on us and their consequences for our liberties and relations with others. Vickers then adds to further answers to his question, ideology as a third powerful force active in the history of public health goal setting, and a fourth, which I'm going to call agency. And he's not terribly optimistic about agency. He goes on to, in the essay, to aver, I think somewhat resonantly, that the history of public health might well be written as a record of successive redefinings of the unacceptable. And in formulating this apothegm, he clearly has in mind conditions of everyday life that we find intolerable and that public policy exists to remediate. And this embodies an idea of progress wherein things that we dislike but routinely tolerate at present become successively unacceptable as we devise ways to improve our condition. Our limits and norms shift historically. But the idea of progress, and Vickers clearly subscribes to this, is not simply linear and incremental. Redefining the unacceptable may mean coming to accept things that we would hitherto want to reject. And he, perhaps unwittingly, I think, offers an example of the way in which this it's possible to redefine what is previously morally acceptable in order to achieve benefits that we have come to seek. When he talks about, there's a nice quotation where he says, our culture accepts some conditions of living which in other epochs would have moved slaves to rebel, such as going to work on the rush hour subway. And I feel that quite vividly, given that I was stuck on the M11 for about 3 hours this morning, as others of you may well also have been. So it's important to ask, I think, what reconfigurations of social relations, what disciplines, what inequalities, and what abrogation of freedoms are implied in making the paradigm of personalization a goal of public health. And then by making this explicit, to take hold of the power to produce new norms and new limits for public health. As I said, Vickers himself is not optimistic about the prospect of agency. He says, I hope I've made it clear that I regard the process by which these goals are set as largely beyond our control, largely but not wholly. Our conscious contribution, though limited, may be crucial. But what he does say brings me back to the conception of public health genomics at its outset, and in particular to underline Vicker's assertion of the importance of both of bringing together disciplines, cultures, and experiences, and, as he says, particularly the inclusion of people who are accustomed and professionally trained to see and answer human questions about people as people. So I began by identifying benefits of personalization as a goal of public health, and I want to restate those, but I want also to acknowledge the challenges that exist on the other side of the balance sheet. In the first place, people, while different, are also complex and inconstant. Health, even their own, may not be their most important priority. As people are not consistent, rational consumers pursuing long-term and common interests, we need political technologies that allow us to reach a coherent policy decisions on which we can base sustainable services. As people have different needs, the needs of some may be more easily served than those of others. We'll need a way of deciding what variations are acceptable and accounting for this in a morally defensible way. And this reaches quite deeply into decisions, for example, about the funding of underpinning research, as well as the deployments of the technologies it produces. Artifacts have politics. The identification of differential risk factors and personalized preventative measures can lead to individuals being held morally responsible for failing to address these. This may take the place of others being willing to carry costs of assisting them in recognition of their common experience, their common features, their common situation. And it may compound divisiveness and structural inequalities given the resources required to engage in self-care. Personalized prevention potentially employs techniques analogous, I would argue, to another area where personalization is often talked about, those of surveillance capitalism, that not only skew options, but seek also to manipulate preferences. Again, we'll need to deliberately define the limits of the acceptable here and regulate those technologies carefully. And finally, health products and services that benefit segmented populations may increasingly be provided as private goods to exploit market opportunities. So my conclusion is that an open and inclusive ethical discourse is needed to resolve the interplay of social norms, individual freedoms, and professional responsibilities at stake in the personalization of healthcare. And as Vickers reminds us, this should involve thinking about the future, thinking seriously about the impact of technology on social relations, and thinking about systems and not just discrete innovations, as well as thinking about others. So addressing this as a matter of policy, rather than leaving it to piecemeal innovation and private initiative, is one way in which we can address the moral paradox of public healthcare, namely, if providing effective healthcare for all means that people should be treated differently, how can we satisfy the principles of justice and fairness that require that all people should be treated the same? These are my acknowledgements. This is my colleagues at the PHG Foundation, and I've indicated those who are responsible for doing the research in the three areas that I mentioned earlier. And I'd like to especially acknowledge Samaya Murthy, who is in the audience today, for her help. And I just conclude by saying thank you again for inviting me.